For our last 20 minutes, we're going to go back to our main application so far, and that's motion. And what we're going to do is consider a new example where the integral really can't be done anymore by hand, even with technology. So what does that mean? That means you have to use approximations. You have to approximate the integral. We've done that before. Left-hand sums, right-hand sums, trapezoid sums. We'll do it again here today. For the homework due Monday, you'll need Mathematica to do your approximations in the way that I'm going to show you. I'll put this Mathematica notebook on Moodle. You can just mimic what I do. You will not have to make a printout. Just get an answer, or get answers if it's a multi-part problem. So the example we're going to consider here is a parametric curve example. And it's kind of one of my favorite kinds to consider. It's called a Lissajous curve. I did suggest to the previous class that they maybe write some things down here, but it might be best just to focus on what I do and what I say. Again, you'll have access to this. I want to define two functions. First of all, x is a function of t and y is a function of t. X will be f of t and y will be g of t. When you define functions first, you need to use the underscore, but once the function is defined, then do not use it. I'm going to make f of t be cosine of 3t. Semicolon just suppresses output. It's not a big deal if it's there or not here, but I like putting it there. So I'm going to put it there. I'm also using the colon equals when I first define the functions. That's in this context not absolutely necessary either. Just an equal sign would be good enough, but I like doing it this way. I'm going to let g of t be sine of 5t. The capital C and the capital S are absolutely necessary. The square brackets are absolutely necessary. Okay, and in fact, the underscores in the definitions are absolutely necessary. R of t, what's that? That's my position vector, which remember by hand, I wrote as something times I hat plus something times j hat, where I hat is called the unit vector, standard unit vector that points in the rightward horizontal direction, and j hat points directly up and is also a unit vector. There's no I hat and j hat in Mathematica. In Mathematica, you've got to enter it like this with, notice the curly braces here, not parentheses. But effectively, we will be imagining this as a point moving. And I could also draw arrows, a position vector as well. I'm not going to do the arrows during class today, but after class, before I put it on Moodle, I'll add some arrows to the picture, some vectors. V of t is going to be the velocity vector. It's the derivative of the position vector, so I can just do this. You can also do an acceleration vector. I'm not going to take the time to do that. I'm wondering, what is the formula for the velocity vector? If I just type v of t with no underscore, because v of t has already been defined, I should see its formula. There it is. The velocity vector's first component is -3 sine 3t, and second component 5 cos 5t. It's the derivatives of f and g. That means the speed function, speed of t, is, remember from a week ago or something, square root of f prime of t squared plus g prime of t squared. That's the same as the length of the velocity vector. What is its formula? It's that. Why? Well, f prime is this. Square that, get 9 sine 3t squared. G prime is this. It put them in the opposite order. Not a big deal. Remember that the integral of the speed is the distance. Copy and paste this here. I could also just type in the speed of t. So this integral should be the distance up to an additive constant at least, with a plus c, where you got to figure out what the c is. We do want dist of 0 to be 0. Put your cursor on that line, do a shift return, thinking, and it gives up. Actually, it took like 5 seconds with the first section to spit back nothing. It gave up. Why? This is just a reality with integrals. Sometimes the integral is so complicated that it can't be done. There's no elementary formula for the answer. It doesn't mean there isn't an answer in an abstract sense. There is a distance traveled here still. In fact, let me quick make an animation of this motion here. You do not need to know what I'm about to show you at the moment. Here's an animation of the motion. It's a very pretty curve, actually. Called the Lissajous curve. And you could ask your physics teachers to make you a Lissajous curve with lasers. They can do that with lasers and vibrating mirrors. They can make Lissajous curves. Notice that the curve does speed up and slow down. In the corner there, it's slowing down. Now it's speeding up into the straightaway. This is like you driving in a parking lot here, right? Looking down on you driving in a parking lot. What's the distance traveled? What's the arc length of the curve from 0 to 2 pi? It's not obvious what it is. Can we approximate it? That's our goal. You can't do it this way because you're not getting an answer. In the first class, I emphasized that I could give this function, this antiderivative, a name. And for fun, I gave it my last name. I called it Kinney of t. Okay, it's not, I shouldn't call it Kinney of t. I should call it dist of t for distance. It's tempting to go ahead and do this with the definite integral button like that. However, that's a problem because when you do the integral symbol, Mathematica tries to do it symbolically first before trying to approximate it. And we've just shown you can't do it symbolically. So instead, I need to use what's called numerical integration. And in Mathematica, the best way to do that is with a command called NIntegrate. Effectively, this represents an integration symbol, except Mathematica doesn't try to do it symbolically. It uses something analogous to the trapezoid rule, or what I'm about to talk about in 5 minutes, Simpson's rule. You plug the function in there, though for sake of clarity, I'm going to change the variable name to tau instead of t, because I'm going to make the t my upper limit of the integral. That's why. How do you make a tau? Well, it's on the writing assistant over here. If you click this button, there's a tau down here. But I also can just do it a more fun way by doing escape, t escape makes a tau. How pretty. How fun. You got to humor yourself somehow, right? When you're doing this. I like making Greek letters. Escape, t escape makes a tau. Do it there, do it here. That's the function I'm integrating. Then you put a comma, and inside curly braces, you put tau, escape, t, escape, comma 0, the lower limit of integration, comma t, the upper limit of integration. The upper limit of the integral is a variable, like we've done before. Shift return. I could plot this. Plot the distance traveled as a function of, now I'm going to use a t from 0 to 2 pi. I could use a tau, it doesn't matter. It's doing a bunch of numerical integrations and then giving me an approximate graph. Then giving me an approximate graph. That is the antiderivative that I'm after. It just doesn't have a simple formula. But it does have a graph that can be approximated. And I can approximate my distance traveled by the time I get to 2 pi. It's about 24.6. But that's having Mathematica do it all with just this mysterious NIntegrate. What we want to do in our last 9 minutes of class is do it ourselves with summations, just like we did a week and a half ago. Is that when it was? About a week and a half ago, I think. Let's remember what we did. We did this before. We let A equal the left endpoint, 0, B equal the right endpoint, which is 2 pi. Notice I made a pi there by doing escape, P escape, pi. Fun, fun, fun. Escape, P escape. And then we did the summations. Left of n, remember that? It's going to depend on n, the number of rectangles you use, the number of subintervals. I'm not going to write things down here because we got to go quick. So you need to pay attention and watch what I do with my hands, try to sort of visualize things in the air. I've got an interval from A to B. I'm breaking it up into a bunch of pieces, n pieces. I'm finding areas of rectangles that approximate the area under the curve. What curve? The speed curve, which I haven't drawn. The motion you saw was not the speed curve, it was the actual motion. Summation button down here. With the left-hand sum, I goes from 0 to n minus 1. The function we're integrating is not called f. F was the x coordinate of the motion. That was the cosine of 5t, but that's not what we're integrating. We're integrating the speed. Speed is the function. I multiply the values of the speed, which gives you the height of the approximating rectangles, times the width of each rectangle, delta t. But what is delta t? It's b minus a over n. Right? Take the length of the interval, which is b minus a, and divide by the number of pieces, and you'll get the width of each piece. And if n is really large, then that's really small. And you have really skinny rectangles in that case. What goes inside the speed function? Watch me here. It's what I call TI. And for left-hand sums, it was the left endpoint of each interval. Take each subinterval, each tiny interval, take its left endpoint to plug into the function to figure out the height of the rectangle. I call it a TI. We had a formula for it. The formula was a plus I times delta t. But delta t is b minus a over n. Use that instead. A plus I times delta t is what that is. The first point, t sub 0, is just a. Then t sub 1 is a plus delta t. T sub 2 is a plus 2 delta t. T3 is a plus 3 delta t. Delta t is b minus a over n. That's a left-hand sum. If I enter it and use it, say with n equal to 100, I get about 24.6, just like I should. If I use a smaller value of n, I don't get so close. But the larger n is, the closer I get. Oops, typo. Get rid of that for the moment. Let's go to the right-hand sum. Copy and paste. Change the word left to right. The only difference is you let I go from 1 to n instead of 0 to n minus 1. And then the trapezoid sum averages these two. These are functions of n, so that's why I need those underscores. when I define the function, but on the left, but I don't use them on the right. Average the left and right hand sums. And we can now look at all these values, say when n is, let's not use 100, let's use 10. And they'll put the slash capital N at the end to approximate them. What's wrong? Something's wrong. This shouldn't happen. I'm not sure what's wrong. Everything looks right. It should not be giving the same thing. Why are they giving the same thing? I've got something different there. Ugh. Is it possible we could be getting the same thing? I don't think so. Let me try a different speed function just to pick something different here. Okay, there it's giving something different. So maybe it's just this particular speed function that for some strange reason they're getting the same thing. That seems really mysterious to me. That's really strange. That is really rude. I don't know what's going on there exactly. Anyway, let's not worry about it. The code does look correct to me. 2 new rules in 3 minutes. Just going to show you the formulas so you can use them on the homework. You should make sure you do the reading. If you've never done math reading, do it this weekend. It'll help you understand it a lot better, and we'll talk about it on Monday. It'll help you for Monday's class a lot better if you do the reading. Even if you've never done math reading before, do it this weekend. The midpoint rule, you can take to be a summation similar to the right-hand sum. I goes from 1 to n, but you make what's inside the speed function be different. And here's a real quick visual. Here's your arbitrary subinterval with a left endpoint, call it t sub I minus 1, and a right endpoint, call it t sub I. You plug in the midpoint into the function to determine the height instead of the left or right endpoints. How do you do that? You average the left and right endpoints. You add them and divide by 2. But what are those left and right endpoints? Well, if we're letting I go from 1 to n, the right endpoint is t sub I, which is the same thing as this thing here. Copy and paste that entire expression after the plus sign right there. And maybe put parentheses around it for extra emphasis, though you don't have to. That's t sub I. What's t sub I minus 1? It's the exact same thing. I'll copy and paste it over here, except replace I with I minus 1. And use parentheses like I just did. Those parentheses right here are absolutely necessary. The other parentheses are optional. This is the midpoint rule. And then finally, Simpson's rule. Well, the trapezoid rule was an average of the left and right. Simpson's rule is an average of mid and trap. However, it's not any old average. I don't take trap plus mid and divide by 2. Instead, I take trap plus 2 mid and divide by 3. What? That's called a weighted average. And the fact that I'm multiplying the midpoint by 2 and the trap by 1 means I'm giving the midpoint rule more weight. I am really averaging 3 numbers here, trap and mid twice. And that's why I have to divide by 3 instead of 2. And that turns out to be the best rule. And when you use these things to get a numerical approximation, do / capital N at the end. And again, I don't know why we're getting the same answers when n was 10 with left, right, and trap. That's really mysterious. I'm going to see if I can figure out why after class. It might be just the particular function, but It was weird. Have a good weekend.